Hi everybody and welcome to today's webcast in partnership with MKS, looking at ultrafast laser technology and micromachining in Europe and beyond. In this live webinar, we bring together a panel of industry experts to explore the evolving landscape of ultrafast laser technology and its expanding role in micromachining. From the latest advances in picosecond and femtosecond lasers to the regional differences shaping global markets, this discussion will provide some useful insights into the opportunities and challenges that lie ahead. My name's Keely and I'm going to be your moderator for today. And I'm very delighted to introduce our panel of experts. We have Marcus Reutering, Vice President Sales EMEA at MKS. We have David Dung, Co-founder and Managing Director at Model Photonics. And we have Christian Vedder, Head of the Surface Technology Department at Fraunhofer ILT. Today's webcast is going to follow a fireside chat format, so I'll be posing some questions to our guests to generate discussion around this topic. If you do have any questions you'd like to ask yourselves, please feel free to do so and submit them. If we don't answer them today, we can pass them on to our panel to ask later. So without further ado, let's get started. So we're going to start with kind of current trends and innovations with ultrafast lasers. So my first question is, with the rise of ultrafast lasers, what do you believe are some of the most exciting emerging trends in photonics that might drive the industry forward in the coming months and even years? Who'd like to go first for me?
All right, then I take it. Thanks, Keely.
It's all right, I was going to pick somebody. That's fine.
I'll volunteer. So just maybe one quick comment. Thanks, first of all, for the introduction, and thanks for David and Christian to join me here on this panel. One quick comment. You introduced me as being from MKS, which obviously is true looking at my background as well. But for those who are not 100% familiar with the situation, MKS is the mother company that has bought in 2016 the companies and brands of Newport, Spectra-Physics, and Ophir. So when talking about MKS in the photonics business, it might not be the most dominant or well-known name, but when introducing Newport, Spectra-Physics, and Ophir, I think it comes clear where we are coming from. So in terms of lasers, laser technologies, I'm mainly speaking here for Spectra-Physics today. In Europe, we are in charge with the entire sales team for Newport, Spectra-Physics, and Ophir in total. But yeah, we concentrate on Spectra. So your question, trends and innovations. As we only have 60 minutes, I try to be a little bit shorter to leave room to the others as well. But, I mean, basically, it is a typical thing. People want lasers to be cheaper. People want lasers to be more powerful. People want lasers to have various wavelengths, and also looking into the pulse lengths to be sometimes adaptable or changeable. So, I mean, if you go to some literature, also a great article recently on electro-optics talking about attosecond, talking about, I think it was septoseconds, something like this. So pulses get shorter, prices should get lower. So we are also seeing a lot of interest in shorter wavelengths. So we are talking DUV, deep ultraviolet and ultraviolet, so 350 and beyond to shorter wavelengths, higher energies. This is basically it. It sounds a little bit easy, but that's where we are coming from. Yeah, moving into milliseconds lasers in the 90s, and then nanosecond lasers afterwards with higher powers, and now nanosecond still be around, picosecond possibly the dominating one, and femtosecond getting a lot of traction in that. So it's, and on top of this, of course, cost and prices. This is how I would describe it as a laser maker. And yeah, there's also applications behind it all the time. But yeah, possibly a little bit the Olympic motto, Citius Altius Mortius, so higher, wider, faster. I think that describes it a lot. And this is also where Spectra-Physics puts a lot of energy into it to increase the energy per pulse and the power for certain wavelengths. More and more is going to UV. So that's from the hardware side. I mean, I would throw the ball over to you, Christian, to see how you see it maybe a little bit more from the application side then.
Yeah. Yeah, I agree. I mean, in mechanical engineering, we always focus on faster, cheaper, better, as you already said. And I think the upcoming technology is very good for high power ultra short pulse lasers. We need to get productivity up. So we know that ultra short pulse lasers are very precise and can be controlled very precisely. But the nature of ultra-short pulse laser ablation is that you only remove a little part. That's where the precision comes from. And by that, it's quite a slow process, very precise, but slow, and we need to get faster. And by this, we need higher power ultra-short pulse lasers and fast deflection beam systems, multi-beam systems, etc., to make use of this power in the future. And I think this is very important.
Thank you. David, you were nodding your head there a lot throughout both of what these guys were saying. Do you want to? Would you like to add as well?
I completely disagree with both Christian and Markus' statements. So it's also what we see. So we're still a fairly young company, like revolutionizing the market of laser beam shaping. So, and this is exactly what Markus said. We're also seeing that the trend is going to UV and deep UV. So the lasers getting there stronger and stronger. So this is where we also get lots of requests to bring that, basically this laser into shape for the certain applications. What Christian said, for instance, increasing productivity. This is a topic where splitting comes into place. So really having multi-spot systems, and also in the micromachining, there's lots of need for customized flat top profiles in these areas.
And what are your views in terms of the future? Do you think ultrafast will become the dominating technology in lasers? Markus, do you want to take that one?
You want a short answer? No. The long answer might be horses for courses. I mean, the discussion about what laser for what application, will there be one technology, etc. I'm doing laser technology since 1989. It has been around all the time. And the answer has always been no. No. There is new technologies coming up. There is shorter pulses, higher powers, different wavelengths, new applications. People are looking for something that has not been done before. We might be developing new lasers for that. Also, dominating technology. Are we talking in numbers? Are we talking in dollars? Yeah, that's always a different point. So I think it will have a very important role, right? That can't be denied. So when we look at lasers, CO2, excimer lasers, and there is all the solid state lasers with the 1 micron regime. There is the pulse laser, CW lasers, 50, 60 kilowatts in cutting versus some microwatts in other applications. From my point of view, it's almost impossible to say there is one dominating technology. Yeah, and let's be clear, Spectra-Physics does lasers in the field of nanosecond pulses, picosecond pulses, and femtosecond pulses to date. We have a little bit of CW lasers for some applications in life and health science, etc. But for material processing, it's mainly what I described. Yeah, and it can go from marking into via whole glass drilling and other applications. Dominating, I don't think so. Important, absolutely.
Thank you. What about you two? Christian, what are your thoughts on that in terms of dominating technology?
Yeah, I totally agree. I mean, ultra-short pulse lasers are still evolving. We are finding new materials. We find new possibilities for high power and fast material processing. But we should not forget that there are already a lot of lasers in the market and in industry and manufacturing. I mean, we talk about nanosecond lasers as a commodity by now. You can buy it very cheap systems by now, and ultra-short pulse lasers are, in comparison, quite expensive. But as Markus already said, prices need to get down in the future and will get down. I think ultra-short pulse lasers will be very important in the future because of the things we already talked about, but there are still other lasers in the market and processes like high-speed cutting of thick materials and stuff like that are quite common right now.
Yeah. David, do you agree?
Yes, and I was wondering, Christian, maybe you can comment on that. So I'm still wondering, so I completely agree. There are different segments where high power multi-kilowatt laser play a role and where ultra short pulse laser play a role. But my feeling is that there are more new segments that can be addressed in the future with ultra short pulse lasers when it comes to really mass, for instance, surface structuring or so, fields which we're not seeing today with lasers. And so I'm wondering if you agree on that, or what's your point of view on that?
Yeah, if we talk about surface technology, I totally agree. So when we're working on the surface of materials, ultra-short pulse lasers will be very important in the future. But apart from that, we still have cutting, welding, and the common manufacturing process that are already in place. And I'm very curious about what will happen in the next 10 years.
Absolutely. So moving on to the kind of the focus areas in micromachining, it obviously continues to be a key area of innovation within industrial lasers. What are your thoughts on the main areas of focus for ultrafast lasers within micromachining, and how, if at all, do you see these evolving? Would anyone like to pick this up first before I point?
Marcus, you probably have the best overview there.
So I should ask you first. Maybe this tells the audience the whole thing is not scripted. So we have not been sitting around and make sure who's saying what exactly. So it's really a panel discussion that's happening now, which I highly appreciate. Focus area in micromachining. Where to stop and where to start, right? So it is a lot is, of course, in the area of surface application, surface structuring, surface modification, surface enhancement, whatever you want to call it. Is a drilling of a blind hole for flex PCBs already the surface changed? But there is functionalizing of materials. There is oxidizing of materials. There is drilling. There is cutting curves in the range of some micrometers. And then again, to come back to the innovations you asked before, it is the wavelengths that also has an influence on the spot size, right? So if we want to get narrower and narrower in terms of the curves, in terms of the cutting, that's an important point to get to shorter wavelengths, because you can focus them to a smaller spot. And if we look into also semiconductor business, where micromachining is applied a lot, these things are getting more compact and more compact. The actual size is 2 nanometer nodes for the classic, no, not a classic, but for the latest technologies using the EUV. The lithography cannot be longer done with lasers because they're simply too big spots. But it's getting smaller and smaller, more micro, and we need to have smaller curves, smaller holes in drilling. And again, I mentioned functionalizing, surface cutting, it's thinning, ablation. All of these are typical things. Maybe the first, I don't know, Kristen, if you would agree, but the first major application in micromachining I learned about was drilling of diesel injection nozzles many years ago, or one of the drivers for this technology maybe. But now it's so wide, it's hard to really say what's driving the focus in terms of micromachining. And let's not forget about applications which are not necessarily micromachining, but use ultra-fast lasers as well, even in bioimaging, microscopy, and other things. So it's a little bit tough to really pick some of the applications, but we see glass materials, we see silicon carbide, we see various plastic materials, we see even metal on some areas, so cutting the battery foils, which are made from copper and aluminum. again, where to start and where to stop. But yeah, we are making the lasers and see what our customers do. But I think Christian and also David are more involved in the development of some applications, even the ones that are emerging new. You also asked that question, how they will evolve. So with that said, I would pass it back to David this time to switch row.
Pass it back. David, what are your thoughts?
The Spectra is a great and big company, so there's lots of well-known experience. So from our side, we see when it comes to need, of course, where beam shaping gets very interesting. So we see, or we've seen in the past, that just increasing laser power, for instance, was a key driver in ramping up productivity and getting stuff done, basically. But now when it comes to the quality and also the productivity, it's getting more and more key to have the right distribution and really laser intensity distribution at the workpiece. And as Marcus completely said, and I completely agree, the wavelength is getting smaller. So there's a lot of smaller features, which is especially in this, I would say, interesting for the semiconductor industry. So for instance, also display manufacturing, where the trend is really going to mini and micro LED production, which is still a challenge for the whole industry. Their lasers and deep UV lasers, especially, I would say, are a key driver to get that done. And there you really need flat top profiles that are very small and precisely at the size of the pixels, can be rectangular shapes, for instance. So I see definitely there is a huge benefit in micromachining. This part we're seeing, but also like microstructuring, surface structuring is also a big field. Yeah.
Thank you very much.
Maybe David, sorry, can I add a question from my side? I mean, you are working on high power applications. You're working on ultra-fast applications. As Meedle Photonics, being a young company, developing company, can you talk about where you see the major customer requests at the moment? Is it more in high power? Is it already in ultra fast? What's driving Meedle Photonics?
I would say it's both. So it's both macromachining and micromachining. So we're concentrating on material processing. So of course our beam shapers could also be used in sensing, for instance. But one major advantage of our technology is that it's really made for high power, high energy, and it's very versatile and long lasting. So it can withstand these high energies also at very short wavelengths, but also multi-kilowatt power in terms of cutting or welding, which we see. So I would say at the moment it's a tie. Yeah? So we have both areas which we have customer requests. Of course, the beam shapes are quite different. So in the ultra-fast regime, we see much more splitting and really diffraction limited top heads, so as small as it can get. So the precision there is really key. Then on macro machining applications like welding or cutting, you see more ring core structures, larger top, flat tops, ring geometries. So it's a bit different from the beam shapes that are needed in these applications. But I couldn't give you an answer right now if there's will be a winner there. So I see the industry is having both lasers types in use basically, and there are also both types as need for beam shaping.
Great, thank you.
Thanks,
and just to you, Christian, did you have anything to add as well on that?
Well, I mean, Marcus already said, microelectronics, semiconductors is a very important field. We just had a little market swoop in that area. So removal processes, exposure, bonding processes, reforming processes. There are quite a lot of laser steps, processing steps within manufacturing and semiconductors. But apart from that, we also have health and bioanalytics. We have additive manufacturing. We have energy, for example, structuring surfaces of bipolar plates and ablation of compound bipolar plates. These are all application areas which drive from the market side from the application side, the development of ultra-short pulse lasers regarding higher power and higher pulse frequencies and stuff like that.
Brilliant, thank you. And if we move on to looking at regional differences, what are your thoughts on different industrial applications for lasers between Europe and Asia? Do you think that there are different ones? And if so, what do you think the main regional distinctions in the use of photonics and laser technologies are? Who'd like to go first? Marcus?
Okay. No, I mean, as you introduced me, I'm in charge of European sales. Not saying that I don't get a sniff on what's happening in the other areas when we have our staff meetings, etc. So yes, there is a big difference in regional applications and in regional use of the lasers. We have mentioned semiconductors, right? So in semiconductors, if we talk about dicing, if we talk about drilling, if we talk about patterning and whatever it can be, there is not too many high volume semiconductor fabs in Europe. Another application where we use lasers a lot also in micromachining is for example, the photovoltaic industry. Yeah, we haven't mentioned it yet.
Okay.
So next to with this always dominating semiconductor thing, there is photovoltaics, there's biological instruments where we need high precision applications. But photovoltaics, to stick to it at the moment, I mean, Germany was very big in photovoltaic until we were bought off or bought out by the Chinese to some extent. And there is still many applications going into that direction, but with knowledge that we have gained in Europe or Germany, some of the integrators are sitting here. So contractual-wise, we are selling lasers in Europe, and then the complete machine, the turnkey solution, goes to possibly Asia, sometimes America. India is growing. Yeah. So specifically India, part of European territory for us, is something to look at. Yeah, and everybody is talking about this so-called China +1 strategy. So I keep my footprint in China, but I need minimum one additional factory somewhere else. People looking at Vietnam, Malaysia, Thailand, and India. And also for our company, we're looking to factories, for example, in the European Union to do something about that. Maybe it's helping us when trade wars coming up. So regionally, yes, the end user applications are very much different, but in the globalization we see today, they're really factored in everywhere. Yeah, where we sell a lot of lasers, for example, in the field of ophthalmology here in Europe. Yeah, so when you need the cataract operation in the eye or something like this, it's not so well known in some other areas. So it's a dominating application with European makers of these machines where we supply. Semiconductor, again, is different. Photovoltaic is wide. Other industrial applications can be wide. But yeah, the dominating semiconductor applications are more in Asia.
Okay, brilliant.
Yeah.
Christian, sorry, what were your thoughts?
No, I think security for the people that are working with lasers are different in these different areas. So while there is almost there are no laws on using lasers in Asia, you can see all the videos where the people are using high power lasers without any glasses or any security. It's really they have a faster approach to the market regarding manufacturing. They have strong consumer electronics markets, semiconductors. Marcus already said textiles and fashion is there. And in Germany, we are more in the field of what's next, what's the next step. So high standards on security on the one side and emphasis on precision and quality on the other side, and integrating into machines is another thing.
Okay, fantastic. And David, what are your thoughts?
Yeah, I don't know if I can add further insights here. So we also see that most of the semiconductor requests come more from Asia. So this is, I think, where all the big fabs and also, but so Marcus, you said there are also some integrators, of course, in Germany also in Europe, but also there are many others in Asia already. So it's also, I'm not sure actually if how the European market there will evolve. I think we still like innovation lead. But also see that there are lots of cost pressure, for instance, coming from Asia or also from China. So I think we have to find a way as industry to work with that.
Thank you ever so much. We've had a few questions come in now, so putting you guys on the spot a little bit. So the first question is, what are some of the most recent advancement in ultra-short laser technology? And how are they improving micro-machine processes in various industries? We've touched on that a little bit. Is there anything you wanted to add in response to that, any of you?
Yeah, maybe
Christian,
summarizing again.
I'm going to pick on you. Oh, okay, Marcus, you go.
So summarizing again, it is the smaller focus that helps micromachining, lower heat affected zones. We are investigating the number of pulses fired to the surface to make sure we get to the depth of the full cut or whatever it is in time, but not overheating the material. So with shorter pulses and different wavelengths, this is improving all the time to have specific applications and materials not being affected by heat. So only applying a femto picosecond laser is not necessarily solving the problem, but you need to apply it in the right way. What energy per pulse, how many pulses, how overlapping these pulses. And with these technologies, we offer further wavelengths and shorter pulses. There is more applications available. And I think this is improving micromachining. This is advancing the technology. Again, for me, the main application guy in the call is Christian. Sorry to point to you here, but this is how I would summarize it again for that question from Korea.
Yeah, I mean, one thing is taking control of each and every pulse from an ultra-short pulse laser is one thing, but bringing it to the workpiece is another thing. So the correlation between scanning systems and the laser, integrating it into a very valuable and easy to use solution, I think is growing stronger in the market and in the systems we find on the market. So, for example, if you have these scanning curves, scanning vectors, and making sure that each pulse has the same distance to the next one, process optimization and process control is one thing. And I think this all leads to more precision and better quality of the workpiece in the end.
Thank you. I'm going to go to you now, David. If you've got
Sure.
anything you'd like to add.
Yeah, I just wanted to add, really seeing a huge increase in the energy and also the average power, which really is a base, for instance, for scaling the productivity in the end. And also then the ability to bring the light in the shape you really need for the application. So I think this combination, this is really what's driving there.
Excellent, thank you. We've had another question. With the laser technology development being fast in basically every term, the optical systems used to get the most of them for industrial scale purposes, like surface, micro and nano patterning of metallic surfaces, are also advancing at the same rate?
Yeah, actually we're quite working on combining these ultra-fast lasers with ultra-fast scanning technologies like these
polygon mirrors.
Sorry, that's the word I was looking for. So with several hundred meters per second deflection speed, you can make use of these high power and high frequencies in laser processing. And that is very important if you work on large work pieces and would like to ablate a large area, but very precisely. these are very important. I think that we are working on these things to work together.
Because what do you think? So my understanding is that there are still these two routes. One is polygon scanner, like really super fast scanning. The other one is really having a multi-spot approach. What do you think? Who will win that race?
Good question. But there's even a third possibility, like combining these two. So not to rule them out at this point. Yeah, I think it's they serve different needs. So I think one would be for a really big area ablation. I think polygon scanners are quite a good choice if you have very repeating structures that you would like to ablate. Then perhaps multi-beam optics are very good, but I think you always have to judge on each and every case that you're working on, which is the better solution for a specific application.
Fair enough. Marcus, did you have anything you wanted to add?
Not necessarily to add, but I see a challenge there, and so I appreciate the questions and hope more interesting questions to come here on the chat. There is different integrators, there's different end users. They all have different either recipes, materials, approaches, also the performance in terms of throughput. The next one more looking to quality. So let's say between the laser and the workpiece, there's no vacuum, obviously, we are filling that, but this is filled in different approaches, as we have heard, multi-beam and polygon. And it's a little bit, that's not a challenge. It's for us important to have the right laser available that can fire into the beam, the beam system that gets the photons to the workpiece, more or less. And there's so many different. So we try to have the lasers as a reasonable general approach in terms of either beam size, beam quality, and such. And then rely on companies like Needle Photonics. And sorry, David, to say there is others that can do it as well. And yes, there's other laser makers that can do it as well. But we have to build the right coalitions to get the application done. Yeah, and so lasers are advancing to some extent. Optical systems, beam delivery systems are advancing as well. And when we ask the question, will ultrafast be the dominating technology? I think Christian already answered it. There will also not be a dominating beam delivery system. Yeah, if you want to cut apart with the smallest and thinnest curve, not to waste material, you will have a different approach than you have a G8 glass surface in 4 by whatever meters it is, where you have to do a surface enhancement. It will be very different in the approach. And we have to be more or less available for all of that. MKS, respectively, Spectra-Physics, is concentrating on the laser, but looking into in all the possible areas where we can supply the beam to the workpiece. And I don't know if it's known to the community. There is a long discussion about having fiber optics on short pulse lasers. Now, that's more a personal point of view, not necessarily MKS's point of view. I think it will be difficult to have fibers in use for these lasers, but who knows what's happening in 2, 3, 4, or 5 years? Yeah, I mean, when I started in '89, as I said, everything was CO2. And there was obviously no fiber. There was articulated arms with 7 mirrors to be aligned, etc. Then all the fiber lasers came in, solid state lasers. And I have no idea yet what can be the next disruptive thing 10 years as of now, which we have not discovered. Yeah. But the question is great. It's not only to have the lasers ready, we need to have the full system ready.
Yeah. The technology is changing so quickly, isn't it, as well? So, yeah, that's a good point.
That's absolutely right. So I would like to add here. So I think there's still lots of need to get the optical systems developed even faster, because what we see is that many customers, when it comes to the full system in the end, are at the moment working with quite sophisticated systems, the optical systems, to really get the laser to the workpiece in the process. So lots of workarounds, really getting the quality when it comes to very tiny spots and kinds of beam shaping. And so I think we need also this flexibility in technologies, be it scanning systems, which can address various positions at the workpiece, very flexible, or customized shapes, like integrating multiple functionality to keep that optical system really simple in the end, making that simple and affordable for the customers.
Yeah, absolutely. If that's okay with everybody, we're gonna talk about beam shaping, the impact of beam shaping. It's obviously becoming increasingly important in the laser industry. How would you say this technology is influencing current industrial applications? And do you think it has potential for new innovations or further market disruption? Marcus, do you want to field this first?
I can kick the discussion off here. Maybe Spectra-Physics is not making optics for beam shaping. We are making optics for reflecting light, for filtering light, for we use gratings, we make gratings for whatever applications. So we have a huge optical portfolio to offer, some under the brand Newport, some under the brand Ophir, but we are not making beam shaping optics ourselves. My personal opinion, again, is that beam shaping is going to be very important. And as I mentioned, there's various players in the market for maybe also various approaches. Everybody will keep the laser system, as David said, as simple as possible. If I can use a Gaussian beam and do the application, nobody will touch beam shaping. Yeah, there is no need to make it more complicated as a laser system might be anyway. But there is some applications where we specifically need a top head beam profile to make sure that my cutting width or my application is leveled in terms of what's ablated. So not being a maker of these units, we see more and more customers asking for it. And so I would pass this possibly more to Christian for application and David for hardware.
Okay. Christian, did you want to pick this up for us?
Yeah, I can try. So on the one side, you have the beam shaping, what we're talking about, like multi-beam arrays and everything like that. On the other hand, you have very tailored intensity distributions. So in case of really driving efficiency up, you sometimes need a very specific intensity distribution on your workpiece. On the other side, your material, especially if you work with ultra short pulse lasers, they have a threshold in fluence where efficiency is highest, and if you go higher with your fluence, the efficiency decreases again. So in that case, you need, if you would like to gain efficiency and productivity, you need like multi-beam arrays to really make use of the ultra-high power short pulse lasers that we have right now. So I think these are really important for the future. I think about beam shaping in special, I will talk about that perhaps later on. Perhaps, David, you would like to take it from here?
Sure, thank you. Yeah. So with Milo Photonics, of course, we are like a hardware producer. So we're really producing beam shapers customized for the certain processes of our customers and what they really need. So, and we see definitely that you can really increase the productivity there tremendously. So we've seen laser systems where with using our beam shapers, we have ramped up the productivity of more than 10x, which is really fascinating doing that. And I think that's the impact beam shaping can do. And so we at Milo Photonics, we see basically three different parts. One is like, I would say classical beam shaping where it comes to flat tops, ring core structures. So really a 2D distribution at the workpiece. Then the second pillar, so to say, is everything splitting. So really like approaches to also enhance productivity. But also there's a third one, which I find quite interesting, is making laser process in the industry even more stable. So for instance, we can also elongate the focal depth of a beam without like increasing that tremendously, the focus spot. So keep the focus small, but making it more propagation stable. Because we always see in these optical systems thermal drifts and other effects. So many processes at the moment in industry still suffer that you have to really control the environment where the laser hits exactly, quite sophisticated. And so we believe that also this can be one major impact in the industry by some kind of laser beam shaping, making the focus more stable. Yeah. So I completely agree with Markus. Don't over-engineer it. If you're okay with a Gaussian beam, that's great. But here's the question: can you maybe elongate the Gaussian to get more stability?
Yeah, yeah, that makes sense. Keeping on the topic, has the variable beam shapes changed the landscape for measurements? Like the applicant wants to know power level in each of these segments. I guess that would be for you, David and Christian again. Which one wants to field that first?
From the OFIR side, right? So from the measurement.
Yeah, maybe I can kick it off now, switching the brand inside MKS from Spectra-Physics to OFIR Photonics. So we have the full coverage of all measurements. So sometimes we say we produce light, we manage light, and we measure light in the MKS, the Photonics division. So OFIR is, of course, for measuring. Yeah, there's more people coming to this. It has not been seen so much on the ultrafast side for the measuring. We see it from people where we measure the high power lasers. There is ring lasers, there is ring focus created from beam shaping and others, and people want to know, how does my beam look like? So we have, of course, solutions to measure a ring beam and tell them what's the acoustic of your ring beam, and what's the ratio of power in each of the segments. That's something we have. We have not seen it so much on the ultra-fast lasers. And maybe I would again throw it over to David. Is these ring structures and such that we see in high power lasers also for the reduce of sputtering, for copper welding, is this something you see in ultrafast as well, or is ultrafast really for beam shaping dominated to create a top hat yet?
Yeah, I think that's a really good question. Actually, I'm not aware that we've used the ring core system so far in ultra short pulse laser. So that's very much focused on micromachining, like especially welding copper, which also other solutions like multi-core lasers, for instance, are used quite commonly. So I don't know. So I would say in the macro machining part, this particular shape is not so much of interest at the moment. I would say it's more flat top that we see in different variation. Also other shapes which can be quite different, but somehow some intensity profile there, which is flat on the top, more so to say. So I also find this measuring of the beam shapes quite interesting. I agree, it's also most of the time in the macro machining, but I guess that will be also a topic in micro machining. I see two challenges there. First, when it comes to really beam shapes, for instance, in the UV and the deep UV, which are diffraction limited, it's quite hard to measure these precisely. I don't know if there are already solutions at OFIR. Markus, maybe you can comment on that later. And the second one is that the specifications are still, there are like no standard specifications for that. So it's our understanding at the moment in the industry, like every one is talking about different in specifications there when it comes to homogeneity of these beam shapes, the characterization of the beam shape in general, like edge steepness. So there are different kinds to characterize that. And there's like no common language, standardized language throughout the industry at the moment. And I think going really further, developing this further, we need some kind of standards there to talk the same language. Yeah.
Great, thank you. And Christian, did you have anything to add on that?
No, I think from industry side, the most questions come in regards to is what is the quality of the part that we're working on. So knowing your intensity distribution and everything is very important for developing a process, but in the end, the part has to be right. So in that case, I think the question from industry side, perhaps there's another opinion from the audience here, is merely is the whole rectangular, does it go through each time, and more things in that case.
Great, thank you. Before we move on to our next question, I just wanted to highlight that we've got around 15-20 minutes left of our webcast. So just to remind the audience, don't wait till the end to submit your questions. We don't want to miss you out. Don't miss this opportunity to ask these guys your questions. Actually, for you again, Christian. Yes.
Sorry for dropping in again. It's not scripted. We are following.
No, we like
topics,
that.
Yeah. So I would like to possibly challenge Christian from the application side a little bit here. So as you know, we are making O4 power meters. We are making O4 beam profilers. When talking about a micro application, micro machining, also it might be interesting for the audience. What do you think is possibly the most important parameter, or the most important parameters in a certain role? What do you think is most important? Is it the energy per pulse, the pulse lengths, the fluence, the wavelengths? Can you say something to that? Is there a ranking from your side, being the application expert?
In this case, I would have to answer all of them, because it's, as always, it's so highly material dependent. What is the driving factor to reach your accuracy and the goal on the workpiece? So, I mean, the strong advantage of ultra-short pulse lasers is that the wavelength, or not the wavelength, but the short pulses are relatively independent from the material that you work on. So in that case, it's in most cases the time of the pulse and other techniques. I mean, you have your frequency. If you drop it too high, you have heat accumulation in your part. If you most of the lasers do pulse bursting, where you can get in a very short time a high number of pulses. And there is the question of what material are you processing? Can it handle these high energy inputs? Do you have any melt that's occurring in that case? And regarding the wavelengths, it's always a question also of precision that you want to reach. We talked about the shorter the wavelength, the smaller the spot you can reach, and the higher the precision. But also differences in the process resulting from the wavelength. So I'm a little bit sorry that it's a very general answer, but it's quite hard to make a general answer, which is the driving factor in that case. It always depends on the material and the geometry you want to ablate or you treat or functionalize.
Yeah, thank you.
Thank you. I'm picking on you again. I'm so sorry, Christian. Question is, what can be created by beam shaping in terms of data science and neural networks, and also the role of AI and spatial light modulators might play in the future? Are you okay to give us a comment on that?
Yeah. But I think digital technologies and artificial intelligence will be causing disruptive change. For now, we know about AI for photonics, so quality monitoring, predictive maintenance, autonomous process optimization. These are things that we are working on for quite some years now. I think the other way around is a rather newer approach, photonics for AI. You already said it, like optical neural networks. I don't know if the audience knows about optical neural networks. Perhaps I can make a short explanation. So the artificial neural network wants to simplify the processes in a brain. So you have different nodes in different areas, layers, like the input area layer and the output layer, and you have a hidden layer in between. And the input nodes are, for example, different sensors that you have in your process. And for example, also the light from your laser. And then you have, they have a different or several impacts on your hidden layer, and then there are decisions made, and they are going out to the output layer. So if we take the hidden layer and take a face mask, for example, you have these nodes as different pixels in a spatial light modulator, for example, and you use light as the information. So in this case, you can alter the phase or the amplitude or the polarization of light. And by that, you can alter the shape or the intensity distribution. So, for example, you start with a laser beam, which is Gaussian, and have a top hat laser in the end. But you only have it in a certain distance to your optical elements. And if you want to have the stability across the distance from the optical element, as David said some minutes ago, you would have to add another spatial light modulator which can correct. And in that case, for example, you can realize these top hat, for example, across a longer distance from the optics, and you have stronger robustness in your process. Also, robustness, and if you add AI, you can also have robustness in your misalignment of these different elements. Next step would also be not to stay in one intensity distribution along a corridor, but to change it, to have in a certain distance, like our flat top distribution, and some millimeters further away, you have another one like a butterfly. And by changing the height of your workpiece, you can get different processing results. And this is all made by AI and all the models that are behind it. And our approach at ILT is that we would like to go from your data-informed machine learning to physics-informed machine learning, where you inherit or implement physical models into your artificial intelligence, and you give all the power to the artificial intelligence. And this is, I think, quite intriguing, and things that we are working on right now.
Fantastic. Did Marcus or David want to ask any questions or add anything on that?
I'm not intelligent enough to follow this approach. But what I've seen at ILT was absolutely impressive, but I can't add to it, no.
Okay, thank you. So if we move on to scientific versus industrial laser applications, so obviously they both serve different needs. What are your thoughts on the key differences between scientific and industrial lasers in terms of design, application, market demand, that kind of thing, and how they're evolving as technology advances, as it advances ever so quickly, as we know? Who'd like to pick that one up first? Marcus, did you want to take that one for us to begin with?
So there's quite a difference between a scientific and a commercial market or industrial laser market. Whereas scientific is more looking to the specs, industrial is way more looking to the cost to have a really high flying differentiation. Also, the applications are different. I mean, I quoted from your electro-optics article that you published, I think, a week or two ago, where people talk about not only femtoseconds, which is industrial application, but about attoseconds and, let me look it up, septoseconds. Yeah, that's what it be. 10 to the minus 21 as the length of a pulse. Hard to follow. So that's a different story. Evolving markets, whereas the industry develops new industrial applications and ask for volume all the time. Scientific customers ask for that one specific laser that suits their needs and applications. So we need more flexible on that. We have products which are dedicated for the scientific market at Spectra-Physics. And maybe some people see us as a maker of scientific lasers, which is true, but today our industrial applications and the revenue or bookings that we get in terms of industrial lasers is way higher. So Spectra-Physics should be considered more an industrial and commercial laser company than only scientific. We have never given up the scientific market, and we will not, for several reasons. One is the student of today is the customer of tomorrow. Yeah, I'm in sales, sorry. So that's one point. The second point is that developments which are done in the scientific market with lasers which are not standard or series products and really push to the edge or over the edge sometimes is helping us to also develop new applications for industrial applications. Yeah, not everything is copied one-to-one. So the scientific market is more challenged by the specs, whereas the commercial market is more challenged by throughput, sustainability, cost, and these factors. Yeah, both important to us, both growing, commercial growing way faster. I have to be honest with that, because scientific market depends a lot on fundings, and fundings are not raising all the time. I think this is a story Christian knows well, because ILT is minimum to some extent funded by government and to the major extent funded by the industry. But it is very important to have both in the portfolio. Sometimes I think a company that does lasers without having the scientific part of it might have an issue in the future. Yeah.
Okay, yeah, that's a good point. Chaps, did you have anything you wanted to add to that, David?
That was a great summary of the situation. So I wish I could, but I think that's a very good situation. And, thank you very much, Markus, for summarizing that well.
Any thoughts from you, Christian, at all?
Well, we are scientists. We are little children that like to play. So there you already have your answer. We would like lasers with like knobs and to change everything, because we have quite a lot of different materials and applications we need to serve with our process development. In the industry, you have a laser that does one task. It has to be robust and easy to use. And I think these are the main aspects that differentiate these two kinds of lasers. But in the end, every scientific laser regarding the transfer into industry needs to do one task, very reproducible and in a very easy manner. And that's what we're working on. Yeah.
Fantastic.
Maybe one quick addition. Yeah, we offer lasers from Spectra-Physics where the initial technical launch was in 1999. We still offer these lasers, yes, with new features and add-ons, etc., but the basis might still be the same. So we have talked about technology is evolving and changing fast, etc., which is, as Christian also pointed out, very true for industrial applications. But these products that we have been selling for decades, I can say now, we twist and tweak them to different wavelengths, different pulse lengths, etc., or give the customer the knobs and buttons that Christian wants to have to play around with these features. Yes, these systems are designed in a different way. So if you want the flexibility, you're not necessarily having the lowest cost. Yeah, I think that's clear. But again, having found the tunable lasers and wavelengths and pulse lengths into a new application, and then we can make the industrial product on it, which then is bringing everything to the most reasonable cost and feature combination.
Yeah, that's very true. So sticking with kind of looking towards the future, we've got some great key players here on this webcast. In your views, and we've touched on this slightly, but what kind of trends or upcoming technologies do you think are particularly worth watching, especially in relation to ultra-fast lasers and industrial applications? Is there anything you see as up and coming, perhaps in the future? Who'd like to field this one first?
I'm really wondering how much this trend in going shorter wavelength will come up basically, or develop further. So really, if there will be more and more applications moving from the infrared to the UV, or to even to the deep UV. So I could think that could be really a trend in micromachining, since the energy is really increasing there. So that's just one point of view here from my side.
Okay.
Yeah, I would have said, or can add, that if we want to watch a trend, I would like to watch the trend of higher powers at low wavelengths. So, for example, our femtosecond lasers today offer 50 watts in 50 watts in UV already. And we might be launching products first in UV and later in different wavelengths today. So IR, of course, is the basis to create shorter wavelengths, but we might launch a product first in a shorter wavelengths, maybe green, but very often now UV. Because as we have mentioned, the smaller focus, the different absorption to material, less heat affected zones, and clearer cuts and applications drives people in that direction. Yeah. So if we look to UV in picosecond or UV in femtosecond, I would say this might be the main drivers. But let's not forget about the classic lasers. So we're actually looking to something where we have considered picosecond, if not femtosecond, for the future, and found now a great application approach with a nanosecond laser. Yeah, too early to talk about, but Christian, for your next ultra short workshop in May next year in Aachen, which I can highly recommend to people listening, that might be a topic we can look at. Yeah, so nano is not dead. Clear message. Yeah, even we talk about ultra fast. New wavelengths, more power in short wavelengths. I think this would be my takeaway from where we stand today.
Fantastic, thank you.
Just to add, yeah, I was talking about the in AI and beam figuring and adaptation. I think these are also very high important technologies that need to go ahead and be in the same speed as the laser technology, because in the end you need to transfer the power that these lasers give you onto the workpiece. And I think besides the lasers, of course, it's very important, we also need to advance the optical systems so that we can make use of all the possibilities that we get from those systems.
Fantastic. Thank you very much. Did anyone have anything they wanted to add to that? I'm conscious we're ever so slightly running over. Okay, perfect. Thank you so much, guys, all of you, for your time today. It's been a really, really, really interesting discussion. I've really enjoyed it, and I've really enjoyed talking to you. So that brings us to the end of today's webcast. It will remain on the Electro-Optics website on demand for the next 12 months, and that's www.electrooptics.com. Please note that the live Q&A won't function if you're watching on demand, but please feel free to forward on any questions that you have and we can pass them on to our speakers from today. All that remains is for me to say thank you very, very much again to Marcus, David and Christian, to our lovely sponsor, MKS, to the Europa Science production team working hard in the background, and to everyone who's taken the time to watch today. Thank you so, so much. Goodbye.
Thank you and goodbye.
Thank you.
Goodbye.